Welcome to Lesson 1 of Module 2. Today, we will be covering Exploratory Data Analysis, or ADA. Understanding your data is a crucial step in any data analysis or machine learning project. We will discuss how to understand your data through statistics and data visualization. We will then discuss two problems you may encounter: imbalanced data and missing data. We'll begin with understanding your data. Exploratory data analysis, or ADA, is a series of operations to analyze a dataset and capture its main characteristics. ADA involves collecting or aggregating data and performing initial investigations to discover patterns, spot anomalies, test hypotheses, and check assumptions. This includes generating summary statistics, graphical and visual representations, such as histograms and plots. ADA also involves processing data to produce meaningful representations for the next steps in the analysis process. By thoroughly exploring the data, analysts can gain valuable insights into its structure, quality, and potential issues. Dataset statistics provide insights about the main characteristics of the dataset. It is generally good practice to understand the number of instances, as the number of rows, and the number of features, which is the number of columns. The slide shows some code examples that assume that your data is stored as a pandas data frame named df. To preview the data, you can call the head method. The shape method returns the number of rows and columns. The info method will display a concise summary of the data frame. Here we include some univariate statistics, which mean they apply to a single feature. If the feature is numerical, you may be interested in the mean or the variance, and you could visualize it using a histogram. If the feature is categorical, you may use bar plots or histograms, and may be interested in the mode, most and least frequent values, percentages, and the number of unique values. You may also be interested in the distribution of classes. The Pandas library provides easy-to-use functions to create histograms and bar plots. In the example plots on the slide, the y-axis, count, shows how many data points belong to a certain section. For numerical features, histograms can provide details about the overall distribution of values. The plot on the left side of the slide shows an example histogram, bins equals 3, with most of the values being smaller than 2000. Bar plots are useful for categorical features. The plot on the right side of the slide shows a bar plot for a categorical feature that is called pet type. The most populated categories are dog, close to 50,000, and cat, close to 40,000. Multivariate statistics deal with analyzing the relationships between two or more features or variables in a dataset. Correlation is a measure that quantifies the association or dependence between two random variables or features. It helps determine if there is a linear relationship between the variables and the strength and direction of that relationship. To calculate the correlation coefficient between two features, you can use the code df_feature1, feature2. Corn your data frame. This will give you the correlation value, which ranges from -1 to 1. A value close to -1 indicates a strong negative correlation, 0 means no correlation, and a value close to 1 signifies a strong positive correlation. Another way to visually inspect the relationship between two features is by creating a scatter plot using the code df.plot.scatter, feature1, feature2. This will plot the values of one feature against the other, allowing you to observe patterns, trends, and potential correlations between the variables. Scatter plots are particularly useful for identifying linear or nonlinear relationships, as well as detecting potential outliers or clusters in the data. Visual inspection with a scatter plot provides a quick look at the association or dependence between variables. The first scatter plot on the slide shows no correlation between the features that are considered. The second scatter plot shows two highly correlated features. They are correlated positively, which means that when one feature increases, the other one increases too. If this scatter plot had the opposite slope, where one feature increases as the other feature decreases, the features would be negatively correlated. Correlation matrices are another way to measure linear dependence between features. They provide an easy-to-read representation of pairwise correlations and can be visualized using heat maps. The code example shows how to calculate the correlation between two features using the core function on a pandas data frame. Correlation values range from -1 to 1, with -1 indicating a perfect negative correlation, 1 indicating a perfect positive correlation, and 0 indicating no relationship between the two variables. A negative correlation means that as one variable increases, the other tends to decrease, while a positive correlation implies that both variables move in the same direction. This slide shows correlation matrices that are associated with the scatter plots from a previous slide. The evaluation of the correlations from looking at the scatter plots was correct. The correlation score of the first pair of features is low, close to 0, meaning that the number of classes is not strongly related to age. The correlation score of the second pair of features is high, close to 1, and positive, meaning that height is related to weight such that as height increases, weight tends to increase too. Correlated features may degrade the performance of your model. Ideally, you want to identify highly correlated features and keep only one of the features. If the features are correlated, the ones that you drop are not very informative in the first place, so the algorithm might not suffer much from dropping the features. Dropping a feature or multiple features can improve the training speed and reduce the dimensionality of your model. Simpler models, which are built on fewer features, are usually preferable because they are easier to interpret and implement. However, highly target correlated features, that is, correlated to the price of the book alone, might improve the performance of regression models. One situation you may encounter during ADA is imbalanced datasets. A dataset is imbalanced when the number of samples per class is not equally distributed. This can pose challenges for machine learning models, as they might not work well with classes that make up a small proportion of the dataset. This could then lead to inaccurate predictions for those classes. This is frequently encountered in fraud detection, as only a small portion of people commit fraud, as well as in anomaly detection, as anomalies are rare by definition, and finally, in medical diagnosis. Here we have an example of class imbalance using the Amazon Product Reviews dataset. It shows that the number of 5-star reviews is almost equal to the combined total of all other types of star reviews, 1-star, 2-star, 3-star, and 4-star. The bar chart illustrates this imbalance, with the 5-star rating having significantly more reviews compared to the other rating categories. Learning to classify the other types of reviews is more difficult than classifying the 5-star reviews due to this imbalance. This example demonstrates a real-world scenario where class imbalance can occur, and the challenges it presents for machine learning models in accurately classifying the minority classes. Apart from changing performance metrics from accuracy to precision, recall, or F1 score, other ways to address class imbalance are related to balancing the dataset or the way ML learns from the dataset. Downsampling is one solution. This involves reducing the size of the dominant or frequent class or classes. This is done by omitting samples from the dominant class during training. Upsampling, in contrast, involves increasing the size of the rare class or classes. Duplicates are allowed, so that there are more instances of the smaller class. Data generation, or creating synthetic samples, data augmentation, is similar to upsampling. It involves resampling from the rare class while slightly perturbing feature values to create new samples. One technique to create synthetic data is the synthetic minority oversampling technique, SMOT. Another tactic is to have the learning algorithm pay more attention to the rare class or classes by assigning higher weights to the rare class or classes and lower weights to the dominant class or classes. The logistic regression module by scikit-learn library provides the class_weight parameter to assign weights to classes based on their frequencies. Missing data is another challenge that can arise when working with real-world datasets. It refers to the absence of values for certain features or instances in the data. This can occur due to various reasons, such as sensor failures, human error during data entry, or incomplete information. Dealing with missing data is crucial because many machine learning algorithms cannot handle missing values directly, and simply removing instances or features with missing data can lead to biased models or loss of valuable information. Because most ML algorithms don't handle missing values, you might want to become familiar with a few techniques to handle data that is missing. Depending on how many values are missing in the dataset, and how they are distributed across rows and columns, removing those rows or columns from the dataset might lead to fewer training data samples or fewer features to build your models. That can lead to overfitting or underfitting. Data imputation is another approach that can be used to handle missing data. There are different techniques to implement it, like average imputation, common point imputation, and placeholder. Some advanced imputation techniques are also available, like predicting missing values using ML techniques. One example is DataWig, an open-source library that uses deep neural networks to impute missing values in data tables. For more information about DataWig, see oslab/DataWig on GitHub at https://github.com/oslab/DataWig. You can use scikit-learn Simple Imputer to perform most of the methods that were mentioned on the previous slide. For more information, see scikit-learn.impute.simpleimputer at https://scikit-learn.org/stable/modules/generated/scikit-learn.impute.simpleimputer.html. The Simple Imputer Strategy parameter allows you to specify how missing values should be imputed or replaced. For numerical data, you can choose the mean strategy to replace missing values with the mean value along each column, or the median strategy to use the median value instead. These strategies are suitable for numerical data types. For numerical or categorical data, you can use the most frequent strategy to replace missing values with the most frequent value in each column. Alternatively, the constant strategy allows you to replace missing values with a specified constant value. This lesson examined different types of features, such as categorical and numerical features. You haven't used these features with any ML model yet in this course. To use them, you need to process and convert these features into a format that machines can understand and learn from. You will learn about this process in the next lesson. Thank you for watching this lesson.